Good afternoon, sir.
Yes, welcome to the session. Thank you. So, uh, I hope you can see the screen. So, is the problem number 1 visible?
Sir, pardon?
Sorry, I
It's
couldn't.
visible only. Visible only. Screen is very clear only.
Uh, Sorry. Okay. So, okay, I couldn't understand what you were saying, but so you can see the screen, right? The problem number 1. Okay. Okay, so let us start. So the concept that is involved for this week's problem solving is the Fourier transformation and inverse Fourier transformation and Fourier series, etc. So actually, in most cases, the Fourier integral that occurs. So in most cases that should be solved using the complex analysis technique that we have learned so far. Yeah, so as I was saying, so in most of the cases, the Fourier integral, uh, I mean, usually is performed through the techniques of complex analysis. Because, of course, in some cases, some functions may be involved that cannot be, the integral for which cannot be treated using the real analysis techniques. So the complex analysis technique for doing this kind of integrations is much more general and versatile. So yeah, let us begin. So again, the problems for these weeks are somewhat lengthy. So that is why I again choose to present handwritten notes. So yeah, I hope you can see the pointers. So please follow that. So the first problem is that we are given a function. So piecewise function that is clearly discontinuous. So we have to first find a Fourier integral transformation for such a function, and then using that representation we are asked to find a value of a particular integral. So you will see that the integral that is given in the question, that is actually almost related to the Fourier integral representation of this given function. So these kind of problems are usually usually solved like as we are now going to discuss. Okay, so let us start. So using the question statement is so using the Fourier sine integral of the function, this piecewise function, find the value of this integral. So we are instructed to use the Fourier sine integral. So let us do that. So first let us recapitulate some theory. So as we have seen in this week's lecture, so if the Fourier sine transformation is of a function f(x) for x greater than equal to 0 is given by this. So if this is the Fourier sine transformation, then the inverse sine transformation is given like that one. So just formula for Fourier sine transformation and the inverse transformation. And in this problem, both of these transformation and inverse transformation will be used. Okay, and yeah, mind the argument. So in both cases, the argument is greater than equal to 0. So it does not involve the negative half of the real axis. So we usually do the Fourier sine or cosine transformation when the integration range is half the real line. So now, we just recapitulate the concept. So now, using this concept, we will first find the Fourier sine transformation of this given function. So the function is pi for x greater than 0 but less than pi, and it is 0 for x greater than pi. And there is and there has been nothing said about what value fx takes for x less than 0. So we will not simply need that information, as we will see. So as I said, so Fourier sine integral or cos integral transformation are usually done when the value of a function is given on the half of the real axis. So here this is precisely the case. So we are only given the value of fx for x greater than 0. Okay, so we can now use the Fourier sine integral. So this is the Fourier sine transformation f tilde s. So this is the formula. Now just substitute fx, and you know, so the original integration range is 0 to infinity, but you see for x greater than pi the function is trivially 0. So only we need to only consider the integration up to 0 to pi, because outside pi fx is identically 0. So this is an easy integration. We have done much more difficult things. So just do that and you will find this result. So root 2 pi 1 by s multiplied by 1 minus cos s pi. So this is the Fourier sine transformation of the given function. Okay. So now let us so this is the first step of this kind of problems. We are actually asked to find the value of this integral. Okay, so now you see, so 1 minus cos s pi divided by s. So what is that? So that, as we have just seen, so that is the Fourier sine transformation of our given function fx. So now as we can recognize, so this thing, so that has been highlighted. So this thing is the inverse sine transformation of this f tilde s, right? Because okay, so that is Fourier sine transformation of f tilde s, where f tilde s is given by this. So this part is f tilde s, and then this is sine sx. So that is the Fourier sine transformation of f tilde s, and Fourier transformation of a Fourier transformation of a function is the function itself. So because this will, so since this is the Fourier transformation of f tilde s, so this result should be the function itself multiplied by some this root 2 pi factors or something like that. But this is actually simply the function fx. So that we will see now. So f tilde s is this, as we have just calculated, Now by inverse Fourier transformation, so as I say, so fx is this thing. So this is the definition of inverse Fourier transformation. This is the definition of inverse Fourier transformation, and then I have just substituted the value of f tilde s in this step here. Okay, and what do we get? So I have simply substituted f tilde s, and then we also have to take care of the this front factor of root 2 by pi. Here it is root 2 by this. So by so after taking care of these factors, so what do you have? So we have fx equal to this thing. Okay. So after taking care of this front factor, we have this thing. So I have just taken this constant factor in the other hand side of the equation, and so this is what is what we were after. So this is the result of this exercise. So the value of this integral that we needed to find the answer of, so this was the integral and the answer of this integral is this. So half fx. So half fx is our answer, and now we will simply substitute what was given in the question. So half fx, so this is pi by 2 for 0 to x to pi, and 0 for x greater than pi, but pi by 4 at x equal to pi. So why it is like that? So as we know, so at the boundary points, the Fourier integral converges to the mean, of the limit, right? So here the boundary point seems like, so at the point of discontinuity, here the point of discontinuity is x equal to pi. Okay, so at x equal to pi, this Fourier integral will converge to this one, half of f pi plus half f pi minus and their mean. So this is the convergence formula for the Fourier integrals at the points of discontinuity of the original function. So using this, so what do we have? So we have f pi plus, so f pi plus means 0 and f pi minus means pi, and that is what I have substituted here, and I have got pi by 4. So yeah, this is our answer. So this is the final answer, pi by 2, pi by 4 and 0. Okay, straightforward. So this was one kind of problem. Okay, and second one, okay, the problem statement is same again, but here the range of integration runs from minus infinity to plus infinity. So the question is using the Fourier integral representation of the function, find the value of this integral. Okay, so the function is this one. So if we look carefully, so fx is 1 minus x square when mod x is less than 1. That means when x is between minus 1 and plus 1, fx takes this value 1 minus x square, and when x is less than minus 1 or greater than plus 1, then fx takes the value 0. So again a piecewise function, and here you see the range of x is minus infinity to plus infinity. So when that is the case, so we have to use the most general Fourier transformation. So the Fourier integral, so other kinds of Fourier integrals that we have just discussed, or that is valid for the half range. is actually called sine transformation or cosine transformation. But this is the actual Fourier transformation. So this is the standard nomenclature. So this is actually called the Fourier transformation. So f tilde s is equal to 1 by root 2 pi integral minus infinity to infinity fx and e to the power isx. So this is the standard definition of ordinary Fourier transformation. Okay, and similarly the inverse transformation is given by this one. So this is the inverse Fourier transformation, just like what we have just seen. So inverse transformation, and only the crucial difference is that whenever you use a plus, maybe you are using this e to the power isx in the definition of Fourier transformation, then you will have to use e to the power minus isx in the definition of inverse Fourier transformation. You are free to choose the other way also, but only thing that you need to keep in mind is that in one case it have to be e to the power plus ix, in the opposite case it have to be e to the power minus isx. That is the only point, and what you will choose is up to your convenience or taste, whatever. That doesn't make any difference. Okay. So now let us find the Fourier transformation of the function that is given in the question. So this is our function, and now we will just simply put this function into the definition of Fourier transformation. So this is the Fourier transformation, and keeping in mind the range of the function, so you see, so as I said, outside mod x equal to 1, fx is 0. So that means we just need to perform this integral from minus 1 to plus 1, because only at this range fx is non-zero. Okay, otherwise fx was identically 0. So simply do this integration. So I will not discuss how to do this. This is a very easy exercise performing real integral. So you should get the final answer as this. So this is our result for the Fourier transformation of fx. So this is the result, 2 root 2 by root 5. So multiplied by this one. So this is our result. So now, but we are actually asked to find a value of a particular integral. So x cos x minus sin x will be x. So let us now actually compare with the Fourier transformation that we have just derived. Okay. And zooming out. I hope it is still visible. So yeah, let us compare. Okay. So this is our result of the Fourier transformation, and let us carefully look at the similarity between this Fourier transformation and this part of the integrand. And this is, as you have suspected by now, this cos x by 2 comes from the e to the power isx part of the Fourier transformation. Okay. So now let us just blindly use the definition of the inverse Fourier transformation. What we will get? So let us just blindly use the definition of Fourier transformation. So this is the definition, and just substitute the value of Fourier transformation. So just substitute f tilde s here, and you will get this integral. So this is actually an integral representation of our original function fx that was given in the question. Now using the techniques of the real integral, so as you see here the range is minus infinity to plus infinity, but in the question the range of integration was 0 to infinity. So we have to convert the range of integration, and for that purpose it is beneficial to use the even function or odd function property of the integrand. So that is a standard real variable technique. So I have done just that. So here let us look here. So this factor, so only this factor, it is an even function of s, right? So clearly this is an even function of s, because sin s is odd, s cube is also odd, so odd by odd makes even, and s cos s is also odd, and denominator is already odd. So clearly this function is even function, and that is what I have used here. Using that property, I have got this result where the integration range is from 0 to infinity. So this is our integral representation of fx. So now I have just so I am now expressing this in the form that has been given in the question. So in the question the integration is given in this form. So I have also taken factors from left hand side to right hand side accordingly, and I have computed that the value of this integral is equal to minus pi by 4 fa. So a sits here, so cos ax. Okay, so you see x will be integrated out, so and the result of the integration should depend only on a, and that is what we have got here. So the result of this integration is minus pi by 4 fa, and the integral that was given in the question is this. I'm sorry. So in the question the integral is this. So cos x by 2, that means we have to substitute a equal to half, and that is what I have done. So substitute a equal to half here, and you will get minus 3 pi by 16. Okay, so that is the final answer for this question. And okay, so you can also verify this answer using the technique of the complex contour integrations that we have discussed earlier. So that will be a very instructive exercise, and that problem is not very straightforward also, but that will be definitely a good exercise to do this integral using the complex contour integral technique. Okay, so that should also give you minus 3 pi by 16. So fine, we have just discussed two problems. Now let us move on to the discussion of Fourier series. Move on to the discussion of Fourier series. So there is something called half range Fourier sine series. So why half range? So I hope you know the significance behind this name, half range. Okay, so find the half range Fourier sine series for this given function fx, which is x multiplied by pi minus x for 0 to x to pi. Okay, for 0 to x to pi. So this is our range and this is our function. You see, so we begin by noting that if x tends to 0 plus is 0, and if x tends to pi minus is 0 as well. So these two boundary values of this function in the given range is actually 0. Okay, and whenever we have this kind of case, so a function in a given range, that have zeros as the values at boundary points, So that kind of functions in that given range can be expanded as a Fourier sine series, and moreover that will not be an ordinary sine series, but that will be a half range Fourier sine series. So see Fn, so let me state that like this. So Fx can be represented by a sine series this. So this is our sine series. Fx equal to summation n going to n from infinity an sine nx, and you see this respect the Dirichlet boundary conditions. Okay, because if you simply put x equal to 0 in this series, so what will you get? So you will get f0 is equal to 0, because sine n0 is 0 and all the terms of the summation is 0, so result is 0. And if you put x equal to pi in this series, what will you get? You will get an sine n pi, and sine n pi is 0 also for n integers, right? So this sine series respects the boundary conditions. Okay. So clearly this sine series is compatible with the given boundary conditions. No, not given, but what we have observed about the boundary conditions. So after writing it like that, now I will just try to find the Fourier coefficients. And how do we do that? We take integration of the both sides of the Fourier series, and that is what I have done here. So I will now integrate both sides of this Fourier sine series with sine mx. So let us integrate this with sine mx, and this is our right hand side, and we know the result of this sine nx. So we know the result of this integral. We know the result of this integral, and the result of this integral is this one. So result of this integral is this one. I hope you are familiar with this notation, delta nm. This is Kronecker delta. So when n equal to m, this is 1, and when n and m are not equal, this is 0. So that is our Kronecker delta, and that means the result of this summation. So using the property of the Kronecker delta that I have just stated, the result of this summation is pi by 2 am. Okay. So that means this left hand side is equal to pi by 2 multiplied by am. Okay. So now I would like to, and clearly since fx is given in the question, so this is a definite integral, and this can be done very easily. So that is how we will now find the values of this coefficient. So the value of this coefficient is this. I have just taken 2 by pi in the other hand side. So the integration is quite easy, and the result of the integration is this one. So this kind of integration occur every time when you do the problems involving finite Fourier series. So the standard real variable integration, nothing tough about that. So the result for this particular fx is this: 4 by pi m cube 1 minus minus to the power m. Okay. And now simply substitute the value of this am in the Fourier, so half range Fourier sine series. So this is our Fourier series, and we will now have to substitute this value of am in this series. So that is what I have done, and I have got this result. So how did I got this result? So one thing, please notice that, so when m is an even integer, so clearly minus 1 to the power even integer is 1, and that means when m is an even integer, this am is 0, and when m is an odd integer, that means here we'll get 1 minus minus 1, that means 2. So when m is an odd integer, the result should be 8 by pi n cube. So actually only the ans for n equal to odd integer has non-zero values, whereas an or n even has 0 values. So that is what I have written here, and I have changed the range of summation accordingly. Okay, and that is how you get this 2n minus 1 here. So I have just substituted n with 2n minus 1, and then the range of n is n going to 1, 2, 3 up to infinity. So okay, that is that. So this is the problem involving half range series. Okay, let us now move on to the next problem. So again, we have to find a Fourier series of a given function, and here the function is x minus box x minus half. So find the Fourier series of this function where x is the, so box x is the greatest integer function of x. So if you are not familiar with it, so it means that box x means the largest integer that is less than or equal to x. So that is the meaning of this. So box x has this property. So this is one of the property of box x. So box x means largest integer that is less than or equal to x. Like 13.5, so box of 13.5 should be 13. Box of 12.1 should be 12. But box of 11 is 11. Similarly, in the negative axis, so box of minus 1.9 is minus 2. So something like that. So the largest integer less than or equal to x. So from this property we reach this one. So this is the property, and that means x minus box x can take values only from and including 0 up to 1, but it cannot take the value 1, as I said. So it can take value 0 up to 1. Okay, and that means okay, so let us now see so we will now see that this function, the function that is given in the question, so this function is actually a periodic function. So how do we find that? So fx is this one. So now substitute fx plus 1. So fx plus 1 is this. I have just substituted x plus 1. So x plus 1 minus this, and box x plus 1, as you have suspected, is box x plus 1, because 1 is already an integer. So box x plus 1 is box of x plus 1 is box x plus 1. So that is what I have used here. So plus 1 here, and another plus 1 comes from this inside of this box, and those two cancels, and we are left with this. We are left with this one, and that is equal to fx, and that means we have this periodicity property. So if x plus 1 is actually equal to fx. So this is the property. This is the periodicity property. So since it's a periodic function already, so we can of course express it as a Fourier series. So is already periodic function. So Fourier series, and as we have seen, the period is 1, so the Fourier series will be of this form. See, because the periodicity is 1. So this is our Fourier series, the most general form of the Fourier series of a function that has periodicity 1. Now we have to again find the value of these coefficients. So that is standard exercise, and you know how to find these coefficients. So like to find the coefficient an, we have to integrate from 0 to 1, or take the integration of this function.
Sir, excuse me, sir.
Yes.
Sir, you have written an into cos of 2 pi nx only it will come. No, you have written sin 2 pi x. A in terms of cos, no.
That does not matter actually.
It is a Fourier series. It means you have write it like this way only, no.
Well, that doesn't matter. I mean, I have just changed the name of A and B. That does not matter actually. Yeah. So what you have to do is name anything you want, but do the mathematics consistently. So to find this value an, so you see we have to do these integrals. Yes. So we have to do this integral to find the value of an, and we have to do this integral to find the value of bn. This involves cos, and for a naught, this is given by this 0 to 1 fx, and this integral is very easy. So let us start from a naught. So do this a naught first. So I have just substituted fx here, and now we have to use the property of the fx. Okay, so in the integration range 0 to 1, so box x is 0, right? Because all the x are between 0 to 1, and between 0 to 1, what is the integer? Like for any x that is between 0 to 1, what is the integer that is, what is the largest integer that is not greater than x? So that is 0, of course, because any value of x in this range, box x will be 0. So that is what I have put here. So box x equal to 0, and now do this easy integration, and this will give you 0. So similarly here also, again, so to do the an integrations, again I have so this integration is what we need to do to find an. So, and again I have used the value of box x in this given region, that is 0, and now we have to perform this integral, and do that, and you will get this answer. So this is the answer for an. And similarly, if you proceed in the similar line for bn, so this is bn, so this is bn, and this is the complete calculation for bn, and finally you should get bn equal to 0. Okay. So bn equal to 0, a naught is also equal to 0, and an is minus 1 by pi n. Okay, now we will just substitute these values in the Fourier series. Substitute these values in the Fourier series, and you will get this result. So this is our final answer. This is the Fourier series. So one interesting thing is that, so So this is the integral this is the Fourier series representation of fx. Now if we put x equal to 1 by 4 in both sides, okay, so let us put x equal to 1 by 4 in both sides. So I put that x equal to 1 by 4, and what was x? X was this one. So x was this one. If you put x equal to 1 by 4 here, that means here 1 by 4 minus 0 minus half. That means the value is minus 1 by 4. Okay, so f at x equal to 1 by 4 is minus 1 by 4. That is what I have written here, and that is also equal to the Fourier series representation of fx. So this one, so I have simply put x equal to 1 by 4 in this Fourier series representation, and that is how I have got this sine pi n by 2. And now substitute so now use the values of sine pi n by 2, and you will get this series. So if you use this value of sine pi n by 2, you will get this series summation. So this series summation, so there is some factor of minus 1 by pi here. Take that on the other hand side, and you will get this infinite series representation for pi. So this is one of the infinite series representation for pi. So pi by 4 is equal to this infinite series. So using this Fourier series, so you can actually prove these kinds of series representation of transcendental numbers. So you can also do pi square, pi cube, pi to the power 4. All of these so series expansions for all of these things can be found using this Fourier series representation. But you have to choose the function fx accordingly. So I think if you choose fx is equal to x square and impose some periodicity condition, so I think that will give you the representation of pi square. Okay. Another thing is that, so from here also in the problem 3, so in problem 3, so if you put x equal to pi by 2, yeah, from this problem itself. So if you put x equal to pi by 2 here, that means you get f x equal to pi by 2 is equal to pi square by 4. So here it is pi square by 4. You will get pi square by 4 in the left hand side, and in the right hand side you have sine 2n minus 1 pi by 2. Okay, and that will give you infinite summation representation of pi cube. So take this 8 by pi in the left hand side, and you will get pi cube by 32 is equal to this series with x equal to pi by 2. So you can play this kind of games. So from this problem you will get the series representation of pi cube by 32. Okay, so that was an interesting observation. Now let us move on to the next problem. Okay. So moving on, so this problem is find the solution of the integral equation. So this is our integral equation. You see what you need to find the solution of. You have to find fx. Okay, so you have to find fx, and there is this parameter a, and it did not occur in the left hand side, but it somehow occurs in the right hand side, this a parameter. So let us see how to do. But as you can recognize already, so the thing that is highlighted, so it is already Fourier cosine integral representation, right? And that is also over the half range. So this is the so apart from the factor of root 2 by pi, so this is the Fourier cosine integral representation of the function fx, and that is given by sin as by s. So since the Fourier integral Fourier cosine representation is given already, so how can we find fx? So we just need to invert the Fourier integral transformation. So let us now do that. So inverting the Fourier integral representation, we get this one, and this 2 by pi factor in front, so it takes care of this root 2 pi things. So root 2 by pi things, and I have put here x greater than 0 because that is what was notified in the integration region. So for x greater than 0, fx is of course the inverse integral transformation, and that is given by this one. So this is the inverse Fourier transformation, and that will give us fx. So now we'll also do the inverse integral transformation over the half range of s. So s runs from 0 to infinity. So now I have used this trigonometric I have used this trigonometric identity. So that this step leads to this one, and then we have to do, so this is actually the integration that we have to perform. How to do it? So this is sin s, so sin ps by s, this part. So these kind of integrations can be done using complex analysis techniques, right? So we have seen this kind of integrals before, so let us use the complex analysis technique. And since this is a half range, so yeah, let us now look at the complex analysis technique. So how to perform this? So consider this integration, sin kx by x. So this is the integration region. In the left hand side it is 0 to infinity, but in the right hand side it is minus infinity to plus infinity. I have used the even function property of the integrand, and to take care of this change of region I have put a factor of half in front of here. So this is nothing but the even function property of the integrand. And now this is the real integral, and we would like to calculate this real integral using complex analytic technique. So what to do? So let us consider this complex integral, right? So e to the power I kz divided by z, complex contour integral over the contour C, where the contour C is this one. So the specification that k is greater than 0 is very important here. So when k is greater than 0 in this integration, so we can choose this contour, and when k is less than 0, we actually need to choose this contour. So depending on values of k, we have to choose the contours accordingly. Okay, and why is that so? Because to do the real integrations using the complex variable technique, so we like to find the segments of the complex closed contour which may give zero result identically. So when k is greater than 0, so that means, so how we do this? So let us first consider k greater than 0. So over this complex contour, So the integrand has singularity only at z equal to 0. Okay, so only at z equal to 0, but we have chosen the contour such that this z equal to 0 lies outside the contour. That means inside the contour, this integrand is an analytic function, and that means by Cauchy integral theorem, this integral should be 0. Okay, this should be 0. So that is what I have written here. And now I will express the complex contour integral in terms of different segment of our contour. Okay, so first let us look at the big semicircle. So the semicircle that has infinite radius. So put z equal to r e to the power I theta, where r is going to infinity, and z is r e to the power I theta. Use dz, substitute here, and you will get this. And see, so this is the large semicircle part, and now this is the small semicircle part. So this one, so this semicircle, so the contribution of this semicircle is captured in this one. So again, get z equal to rho e to the power I theta, but rho is now tending to 0, and this is the integral. Substitute rho e to the power I theta and do all these things, and then now this is the contribution from this left line segment that lies along the x-axis, and this last contribution is from the right line segment that also lies on the x-axis. So this is the separate contribution of the 4 parts of the contour. Okay, that is fine. And now let us look at the first thing. So the first contribution. So this is the first contribution. This is the first contribution, and I have just written e to the power I theta as cos theta plus I sin theta here. And you see, when r going to infinity and sin theta, so we are in the upper half plane, and in the upper half plane, as we know, sin theta is positive, right? Sin theta is positive. So let us look here. So this thing, so e to the power I kr plus multiplied by I sin theta. So this one. So now, as we just seen, sin theta is positive on the upper half plane, r is positive, and k is also positive. That means this is e to the power minus kr sin theta. So I multiplied by I is minus. So that means e to the power minus k sin theta multiplied by r. And at the limit r tends to infinity, this goes to 0, of course. So that means the contribution from the large semicircle is 0. Okay, 0. And now this is the result from the small semicircle. The integration is very easy. After doing the integration, I have also taken this in the other hand side, and thus, so okay. So this is the result. This is the result of the integration. I have combined the contribution from the 2 segments that lie on the x-axis. So I have combined them to get this. Okay, and that means we have this result. So minus infinity to infinity dx sin kx by x for k greater than 0 is pi. So because we have just take We just have to compare the real values and imaginary values in the left hand side and right hand side in both cases. So in the left hand side the real value is 0, so we only need to compare the non-zero imaginary values. That is what I have done, and I have got this. So this analysis is for k greater than 0. And similarly, for k less than 0, we have to choose this contour. Why? Because for k less than 0, this semicircle will actually give the 0 contribution. So had we chosen the upper half contour, the large semicircle, that would actually diverge for k less than 0. See how we get 0 result here. So again, let us write it like that. This is the contribution from this large semicircle of infinite radius, and then I have just used this one. Okay, I have written this. So easily this is this one. So now e to the power minus kr sine theta, and you know sine theta is negative in the lower half plane. Sine theta is negative in the lower half plane, and k is also negative. Okay, so that means k sine theta must be positive, and r is also positive. So that means e to the power minus some large positive number, and that is 0. Okay, so we somehow need to find a positive number, a large negative number in the exponent of e. So that is our goal, and we need to choose our contours accordingly. So that is why you choose k less than 0. That is why you choose this lower half contour for k less than 0. Okay, and if you do the all previous steps, so you will get this result. So this is another result, so quite important result. So sin kx by x for k less than 0, the result of the integral is actually minus pi. Okay, the result of the integral is minus pi, and now, and for k greater than 0, the result is plus pi. Okay. So now we will simply use that fact and substitute the value of these integrals. So let us do that. So a and x are both positive. A is positive, that was given in question, and we are doing the positive side, right half plane. That means x is also positive. So the value of this integral, so this is always pi by 2. This is pi by 2, and for this right one, so when a is greater than x, so that means when a minus x is greater than 0, so that will give us pi by 2, as we have just seen. So that is that. So one of this result is this. For x greater than 0 but less than a, our result is this. And similarly for x greater than a, that means this sign. So for x greater than a minus x is negative, right? So when this is negative, we saw the result is minus pi by 2, and just substitute this result and you will get this. So this is the result. So this is actually incomplete result. The complete result should also include the point x equal to a. That is what I have done in the end. So if you put f equal to a, that means the right integral will be simply 0, because sine of 0 is 0. Only the first integral survives, and 2a is positive, and that gives half. So that is our final result. So this is the final result. So fx is 1 for x less than a, half for x is a, and 0 for x greater than a. So yeah, that was a quite involved problem, so mainly due to the complex analysis technique. So it is already 4, but I wanted to discuss another 2 problems. So yeah, now I will simply give an overview. So how to do this problem. So using the Fourier transformation, find the solution of this PD. So this is the PD in the region x greater than 0, t greater than 0, okay, and with boundary condition. So we are given 3 boundary conditions. So one is this one, del u del x at x equal to 0 is 0. The second one is this one, uxt is bounded. So this is not actually a boundary condition but simply a condition. So our solution is needed to be bounded. And the third one is this one. Okay, so this is actually an initial condition. So what is the value of our function at t equal to 0? So this is the initial condition. Okay, now let us go. So first we have to do the Fourier transformation. So first look at the boundary condition. So this boundary condition is del u del x at x equal to 0 is 0. And looking at the form of this Fourier transform, so in this boundary condition, and keeping in mind that we have only access to the half range, so we see that we have to use the Fourier cosine transformation, because so if we take this Fourier cosine transformation, okay, and then if you take del u del x, so if you take del u del x of both hand side, what you will get? You will get sin kx in the right hand side, okay, and sin kx, if you put x equal to 0, that will give you a 0 result, identical. So this is why here we have to use the Fourier cosine transformation. So had we used the sine transformation, so there would have been sin kx, take that derivative, you will get cos kx, but cos kx at x equal to 0 is not 0. So that would not have been compatible with the boundary condition. But if you take the cosine transformation, that will be compatible with this boundary condition. So this is the boundary condition. So this is the cosine transformation. Okay. Now let us substitute the cosine transformation in the PD itself. Substitute the cosine transformation. So this is the PD del u del t equal to del 2u del x2. So substitute this series in the PD, and this is, so del u del t give you this result, and u tilde dot is nothing but, sorry, there would be a tilde. So this is del u tilde del t. And from the right hand side, so we have to take derivative twice with respect to x, and this will give you this result. Now bring things in the same side. So this is your differential equation. So this is your equation now. And what is that? So this is nothing but, okay, so what can we say from this equation? So this says that the Fourier cosine transformation of this function that is highlighted is 0. So the Fourier cosine transformation of the highlighted function is 0. And that means this highlighted function must be 0 itself. So this function is 0 itself, because we can of course invert this Fourier transformation and get 0 also. So inverting this Fourier cosine transformation, we get this 0, and we can simply, so this is a simple differential equation. So first order differential equation, and you solve it like that. So this is the solution of differential equation. AK is nothing but a constant but depend on K. The most important point is AK does not depend on T. So this is our U tilde K. Okay. Now let us use the boundary conditions. So our boundary condition was something. So we were given Ux at t equal to 0. So we know what that function is. So now let us first write this like that. So ux naught is this. So I have just put t equal to 0 in our Fourier cosine transformation. That will lead to this result. And what have we just found? And u tilde k naught, and u tilde k naught is nothing but ak, right? Because if you put t equal to 0 here, you will get u tilde k naught is equal to ak, and that is what I have written. So ux naught is actually this function. Ux naught is this function. So now what do we see? So if ux naught is this function, that means ak is the Fourier cosine transformation of ux naught. So this is a statement of Fourier cosine transformation, right? So now again invert the Fourier cosine transformation to find the ak. So that is what I have done here. So I have just inverted the just above Fourier cosine transformation, and I have got this one. Okay, and now I will just use the initial conditions. So this is the formula for ak. Okay, so this is the formula for ak and ux naught. What is ux naught? Ux comma 0 is x for 0 to x to 1 and 0 otherwise. So quite easy function. So ux comma 0 is only non-zero for x going to 0, going to 1 from 0. So use that one, do this integral, and you will get this result. So this is the result for ak. This is the result for ak. Okay. And now finally we have to substitute the various pieces of uxt. So what was uxt? So uxt was cos kx. So this one, cos kx u tilde kt. So now we will substitute u tilde kt. And what is u tilde kt? U tilde kt is this ak e to the power minus k square t. And what is ak? We have just found ak to be this one. And after collecting all these pieces, this is our final answer. So yeah, quite involved problems this. Now the last one. Okay, since it's already 4:10, I don't feel like doing it anymore. So, okay, moreover, I have used a different technique here also. So, using the finite Fourier transformation, find the solution to the boundary value problem. So, this is this. This is the partial differential equation, and we have three boundary conditions. So, okay, one thing is that, so this should be the correct boundary condition. So this is not correctly written in the assignment. So this should be the correct boundary condition, the condition 1. Okay. But condition 2 and condition 3 are correctly written in the assignment. Please note it from here. This is the correct boundary condition. So using these three boundary condition and the partial differential equation, we have to find the solution. So I have used here a technique called separation of variable, but you should not actually use here. So on note, the final answer is this. So in the last line you can see the final answer. Okay. So to proceed, you should actually use the half range sine series. So from this, so there are two boundary conditions. U x equal to 0, so the range of x is 0 to 2. 0 to 2. Range of x is 0 to 2, and u 0 comma t. So the value of uxt at x equal to 0 at all time is 0. And similarly, u t comma 2 comma t, so the value of uxt at x equal to 2 at all values of t is also 0. So again, as I have said before, so in these kinds of problems, when the value of the function at the boundary points is 0, you can use the half range sine series. Use the half range sine series and feed it to the differential equation and satisfy these boundary conditions. You should get the final answer, this one. So I am not explaining what I have done because I have used a different technique. So this is called a separation of variable technique that I have used, and that is a general technique so to solve partial differential equations. But you should try this using the half range sine series. So write a half range sine series, feed it to the differential equation, and find there will be some differential equations on the coefficients. Try to satisfy those boundary conditions on the coefficients, and try to match the half range sine series for this function also, and you are done. So this is the result. So you should try that. So okay, so that finishes our discussion for today.